Hello, everyone, and welcome to today's TED Talk on modular chiller strategies. My name is Maria Augustine, and I will be the moderator for today's session. Please note that throughout the TED Talk, all phone lines will be muted. This will minimize any background noise or feedback that could distract from the presentation. We will be using the Q&A function. When you have a question, you can submit them through there in the Q&A function tab. We'll be gathering the questions throughout the TED Talk, and we'll leave a little time at the end to answer those questions. We will also be recording this TED Talk, and it'll be available on our website under the resources section. Today's presentation is brought to you by the Northeast chapter. Today's presenters are Albert Stark and Derek Tynan. Albert graduated from Stony Brook University with a BE and MS in mechanical engineering in 2015. Since then, he has garnered 7 years of working experience from various companies in the manufacturing and manufacturers representative market. He currently works at the SRS Enterprises as an equipment sales manager. SRS Enterprises Incorporated is a recognized leader as manufacturers representative of the HVAC products and in the greater New York and New Jersey marketplace. He is also currently an NYS certified EIT and is on track for obtaining a PE license. He recently presented on compressurized heat pump and heat recovery and hydronic systems. His favorite part of the job is hosting presentations for a curious audience, as the teaching learning feedback is a very rewarding experience. He currently is a member of ASHRAE's Long Island chapter, elected to serve in the sustainability chair. His goals in his career and life would be to foster a more sustainable world for the future generations. We also have Derek Tynan. He is the current president of the BCA Northeast chapter. He's an accomplished professional engineer and certified energy auditor with over 17 years of engineering experience, specializing in both new construction and existing building commissioning, energy auditing, and facility assessments. He is also a mechanical engineering graduate from Stony Brook University. He recently presented on leadership skills for forming a team and implementing new construction commissioning and has written several publications for facility maintenance decisions in the fields of HVAC systems, monitoring-based commissioning, sub-metering trends, and has even been noted in the Wall Street Journal. Mr. Tynan has previously supported the Northeast chapter by assuming the role of webmaster, communications chair, and has extensively contributed to the planning and execution of several annual Northeast chapter commissioning summits, which include various cities and state agencies in both the public and private sectors. He is currently advocating for interested members to contribute to a cause that is bigger than themselves by joining the current board at their next Northeast chapter board meeting on October 21st at 12 p.m. Welcome, Albert and Derek.
Hi, everyone. Excited to be here. I'm trying to show my slides. I'm just wondering if they're coming up. Derek, do you see them?
Yep, they're there.
Okay. So hi, everyone. Today we're going to be talking about a modular chiller. I'm going to be talking about design strategies and dealing with variable flow using these modular chillers. And halfway through the presentation, Derek will be coming in and talking about the commissioning process for these modular chillers in new construction and in existing constructions. Our learning objectives today, we're going to start by talking about what is a modular chiller, why do we use it, constant flow versus variable flow in these modular chiller systems, and I will briefly finish off by talking about new technology, air source heat pumps. Well, not new, but it's emerging and getting a lot more popular. And then Derek will jump in. He'll talk about the commissioning process for these modular chiller systems and performance testing methods and criteria. So let's get started. So a modular chiller, we define it as one or two independent refrigerant systems. You can see a picture of this in this illustration right here. This is a modular, one modular of a modular chiller. So this by itself is a chiller, standalone. This is a standalone chiller, but we mount them in parallel side by side to form a modular chiller system. You can see here we have common headers that can connect these modular chillers as into one whole chiller system. And we use a master controller to oversee all operation of all connected modules. So they are individual chillers, standalone modules, but they are controlled as one overall system with one controller. Here is the illustration of that single module bunched up into 6. You can see that that common header connects each one of these modules into one overall chiller system. There's a few reasons why we choose to use modular chillers on our projects. Installation versatility, redundancy, future add-on acceptability, and variable flow minimum GPM, which will be one of the main topics of today's discussion. For installation versatility, you can see one of these chillers can fit through, a single chiller module can fit through a 36-inch door frame. And if you have a roof installation, a lot of the times you could rig it through an elevator and maybe avoid using expensive crane rigging systems. A 70-ton module weighs about 2,200 pounds, and the typical passenger elevator weight limit is about 3,000. So these fit onto elevators, size-wise and weight-wise. Second reason is redundancy. So if I have a 300-ton chiller system and I need N+1 redundancy, in this case, I would need a whole another 300-ton chiller system. If I have two 150 tons and I need N+1, I would need a whole another 150-ton chiller. For a more modular system, if I need N+1 redundancy, I simply can add one additional module for that redundancy. It's a lot less expensive, and installation-wise, this module can be added simply onto the end of this chiller system to easily get N+1. And the main topic, variable flow minimum GPM. So when I use these modular systems, getting a very low minimum flow is much easier because they're individual chiller modules. Minimum flow is generally limited by the combination of the type of heat exchanger used. For example, I have a brazed plate and frame type heat exchanger here, and I need minimum flow in order to get enough flow turbulence through that heat exchanger. So if I have a variable flow system, I can knock down this minimum flow. So I have a design flow that's like our full load performance. If I need a minimum flow and I have 6 modules, my minimum flow is this design flow divided by 6. So we can get a large reduction in flow and therefore saving a lot of energy. To put this in perspective, if I have a large centrifugal shell tube type of machine, and let's say I designed it for around the same tonnage and flow, this chiller requiring 966 GPM, the minimum flow I can get through this unit is 351. Compare that to the modular chiller system over here, where I can get that similar flow down to 162 GPM, almost half as much. And if I use the right combination of shell and tube and maybe a centrifugal into a modular system, so it's sort of a hybrid between these two systems. This one uses a brazed plate with scroll compressors. This middle one uses centrifugal compressors with shell and tube with more leniency on the minimum flow through each module. I can actually get a minimum flow of 94 GPM using this modular centrifugal type machine. So this is one of the biggest advantages of our modular chiller system. We can get very, very low minimum flows. So constant flow versus variable flow. So constant flow is what most old buildings use nowadays. So I take that design flow of 966 and I'm just constantly running 966 GPM through my system, even at low load conditions. And this constant flow system, it's older style, and it's more common in existing buildings or smaller chilled water loops. Variable flow is where I use VFDs on my pumps, and I can vary the flow flowing through my system. Most new construction uses some sort of variable flow, and ASHRAE 90.1 actually requires VFD on pump motors greater than 10 horsepower. There's many different types of variable flow systems: variable flow with conventional chillers, variable flow with modular chillers. We got primary, secondary, We also have variable primary, variable secondary type flow. I'm going to focus today on the variable primary flow because it's the recommended way we control these systems. It's possible to control these modular systems with primary, secondary flow, but you have to consult your manufacturer for recommended approaches for these kind of setups. The variable primary flow is the recommended setup. So here is a conventional chiller with variable primary flow. The key points here is we have pumps with VFDs on the pump, and they could vary the flow going through the chiller and being sent to the air handling units. When we look at a modular chiller system, they can run in constant flow and they could also run in variable flow, but there's a few key differences. So when I look at a constant flow system for these variable flow chillers, let's say I have 55-degree water serving these chillers to be cooled. And this chiller modulates, right? So how it modulates is compressors turn on and off depending on the load condition. So if I have 55 water degree and I have about a 50% load, let's say, that means half the compressors on this modular system are turned off. So if I have constant flow, that means water is flowing through each one of the modules, even if the compressor is off. So if I have, for example, 55-degree water going in here and the compressor is off, that means 55-degree water comes right back out this way. So if half the compressors are off, that means half the water is chilled to 45 degrees and half the water is chilled or not chilled and is coming back out at 55 degrees. So what we have here is a mixed chilled water supply. The 55 mixes with the 45 and serves 50-degree water. So if I have a constant flow system, my chiller needs to modulate and be controlled via return water temperature. It can't control via supplied water temperature. If we want to turn our chiller into a variable flow chiller, what we need to introduce are variable flow valves. So you can see it right here. This valve is put into the header, and it's between the header and the heat exchanger of the unit. So as a chiller compressor stage is off, that means they will shut the flow off in the unit. So if we go back to the illustration, if the compressor is off, that means the water will not flow. The valve will shut off right here and water will not flow through this module. It will simply just pass through this module. And we can, for this 50% load, we can cut our flow by 50%, saving on pumping energy. So these are what these motorized valves look like. And also, by introducing these variable flow valves, we can allow leaving water temperature control. So if we go back to this illustration, no flow through here, that means there's no 55-degree water in the supply header. There's only 45-degree water in the supply header, and we can control our system based off our set point supply water condition. So here's an illustration of a variable primary system with a modular chiller. And the key important items in this illustration that need to be incorporated into design are the modular chiller, the VFD pumps. We have a differential pressure sensor for the chiller. We have a differential pressure sensor on the system side, and we have a system bypass valve. You need all of these components to be successful. How these items are controlling the modular chiller will vary depending on manufacturer. So the important recommendation is to follow whatever the manufacturer recommends. This manufacturer recommends that the VFD is controlled by the differential pressure sensor on the chiller. Am I still presenting? It's my screen is freezing up. Hello? Hello?
You went back to the first page and you're no longer in the presentation view.
Yeah, my screen is blacking in and out. It's kind of weird. Oh, is it back? I think I'm back. Now I'm losing it. Oh, I'm sorry about this. This is an unexpected glitch. One second. Let me try to stop sharing and reshare. Is anything coming up?
You're not in the you're in the presenter view.
Yeah, my screens are just turned off now. This is so weird. I'm very sorry. This is this has never happened to me before. Am I shit? Do you see my non-presenting view now? How's that?
There you go.
And maybe put this off to the side. I don't know if I could hide this taskbar. I don't know if you see my taskbar for Zoom blocking
No,
the screen.
you're showing the display screen now. That's what you're sharing.
So not the presentation?
We see just the presentation that you're trying to share.
Okay, so we're good?
Yeah.
Okay. So control of these systems will vary depending on what the manufacturer tells you to do. So for example, this manufacturer recommends that the VFD is controlled by either the differential pressure sensor by the chiller or by the system differential pressure, and the bypass valve shall be controlled by the vice versa of whichever is you choose to control. So in the top illustration, VFD is controlled by the system DP sensor, and the bypass valve is to be controlled by the differential pressure sensor by the chiller. So the recommendation here is to always follow the manufacturer recommendations, because there's very important notes within how these chillers are selected and designed from the manufacturer. Zooming in on this manufacturer recommendation, you can see that they set the DP transmitter, DP1, by the chiller at 6.25 PSI. So what the system is doing here is, if I could go back a couple slides, as those variable flow valves turn off in each individual module, the water pressure is going to change by the chiller, because the pump's going to be pumping the same amount of water unless it detects anything. So what happens is the DP sensor is going to read that difference in pressure from valves turning on and off, and the VFD of the pump will compensate for whatever pressure it reads. So we need to have the initial setting for that DP sensor to what the manufacturer initially recommends. We also need to incorporate a DP2 sensor into our system. In addition, we need that bypass valve, and that bypass valve needs to be sized for the minimum GPM that's recommended. So in this illustration, the minimum GPM for the system bypass valve is 157.2 GPM. And that's for the chiller only. This number is based from the chiller only. If there's any other components that require higher GPM than 172, you should probably size that bypass valve for any other minimum requirements in the system. And the last item that is highly recommended is that bypass valve for the system needs to have a quick response stroke time. And usually this becomes a problem when they wire that bypass valve to the BMS, and the BMS doesn't react fast enough to any sort of changes in the system. So it's highly recommended. You can wire that bypass valve to the BMS to get a reading, but don't have the bypass valve controlled by the BMS. Have the bypass valve controlled directly from the differential pressure sensors so that it reacts fast enough, and it needs to have a stroke time of less than 60 seconds. So here are the components for a successful design. Fast acting, pressure dependent bypass valve, less than 60 seconds. No, don't wire it to the BMS for BMS control, to get the BMS to control it. It's going to cause a delay. We recommend wiring it directly, the sensor directly to the valve so that it opens and closes as fast as possible and reacts quickly. We want to meet our minimum loop time and our volume for our system. We want to size the bypass correctly. And the chiller DP sensor is going to control the pump or the bypass valve, like we showed in the previous illustration. I have a couple slides on modular air source heat pumps. These air source heat pumps provide hot water in addition to chilled water. And these air source heat pumps are very rapidly gaining popularity because of national legislation such as Inflation Reduction Act. And here in New York City, we have the local law 97, which greatly promotes compressorized heating solutions for building heating over burning fossil fuels. There's several considerations for these air source heat pumps, and one of them is the defrost cycle. So the outside coil of this outdoor heat pump is actually an evaporator. When in heating mode, the outdoor coil becomes the evaporator coil. And that evaporator coil, the surface temperature of the evaporator coil can go under the dew point temperature of the ambient air. And if my surface temperature is below dew point temperature, that means condensation can form. And if you're below freezing point, which happens very often in New York, that means that condensation is going to turn into frost. So you'll have frost forming on the outside of your coil, and it's going to limit the airflow of the coil on the outside, which is not good. We don't want frost forming. So how do we get rid of the defrost on our coil? We have to reverse the cycle. We have to turn this coil into the condenser again and create some chilled water in order to melt the ice on the coil. But if I'm running the system in a reverse cycle, that means, let's say I have a return hot water temperature of 110 and the supply hot water temperature of 120. If I'm running in a reverse cycle, I will actually be chilling water. So my return water comes in at 110, but may leave at 105. A good strategy to avoid this derating is to simply use a modular heat pump strategy where you have one unit in defrost while the rest of the units can pick up the slack. So that's why a modular heat pump approach is very popular for these heat pumping systems. It gives you a level of redundancy for defrost cycles. The last point I wanted to talk about is that these air source heat pumps often have a derate in capacity at lower ambient temperatures. So the colder it gets, the less heating performance I get out of the unit. So these aren't like traditional air, outside air chillers where, let's say a chiller system is designed for 95 degrees, and at 95 degrees, it's going to give you 100 tons, and it's pretty consistent with that 100-ton output. Air source heat pumps can have a very high amount of derating at lower ambient temperatures. You can see on the right column, this is one chiller rated at different ambient temperatures. At 60 degrees ambient temperature, this unit can produce almost 3,000 MBH. But at 0 degrees, I get half the unit capacity. What's the effect? So the effect of this is the flow through each individual active module will always be a constant. But because my capacity decreases, what changes is my delta T. So with these air source heat pumps, we can still do variable flow. It's just that we can't get that consistent supply water temperature because we're at the mercy of the ambient air temperature outside. So our control system needs changed to modulate based on return water and supply water temperatures. But variable flow works in a very similar sort of way with differential pressures, picking up the pressure differences corresponding to the valves opening and closing. So those are the slides I have. Now, if I can hand this presentation off to Derek. Derek, are you ready?
Yes, I am. Thank you, Albert. You just have to stop sharing your screen and I can then share mine.
Sorry, I'm looking for the, oh, there it is. Stop share. Very good.
Okay, Albert, can you see my screen?
I can see it.
All right, thank you, Albert, and good afternoon, fellow BCA members. The commissioning process is most effective when it's started early. Meeting face-to-face and getting all the players to contribute into establishing the owner's project requirements can greatly enhance the commissioning process. Don't just make it a check the box item. When it's establishing or accepting a commissioning scope of work, ensure that the number of commissioning reviews matches the complexity and size of the project. Having the commissioning provider start at 100% construction documents is the wrong approach. That's like bringing in the commissioning provider in once the team has done all the work. However, it's best to understand the commissioning provider should not be looked at as the design drawing gatekeeper or the engineer of record. The commissioning design reviewer is not a peer review unless specifically requested to do so by the owner. The commissioning provider provides value by bringing their experience to the table by adding requirements for testing equipment and by adding field experience input into the design development phase. A successful turnover starts here. The typical misconception is that the commissioning provider is the team, or at best, the team is thought to be the commissioning provider, the controls contractor, and maybe also the mechanical contractor. However, leveraging the abilities of the broader team is key to leading the successful turnover in commissioning. The goal of the commissioning process is for the team to provide successful turnover of the commissioned systems. The commissioning provider should be a leader of this team, so be proactive. Modular chillers specifically require additional support from water treatment vendors, a manufacturer trained representative from the vendor, or the manufacturer of the modular chillers, or a combination of the two. The testing, adjusting, and balancing provider also needs to be incorporated early with the integrated controls vendor. And the team also benefits from having additional field support from the engineer providing construction administration. Finally, the owner-operator personnel should be involved in the process to both better understand the installed system and to provide additional input on how the systems will be maintained and operated. The commissioning process begins with the establishment of the owner's project requirements. The OPR is best established in a schematic meeting, preferably face-to-face. Questions should be answered and documented. This occurs through several meetings through the schematic and design process. However, an OPR is not a basis of design. Detailed design information, such as air exchange rates, are not typically included in an OPR, as those details are determined later and added to the BOD. An OPR is recommended to be created at the schematic phase. The sequence of operations is yet another example of something which will change over time, which is best kept as part of the basis of design and later included into the construction documents where it'll ultimately take its final shape. The team should also include input from facility staff, They should discuss expectations for the BMS, such as alarm reporting, as well as facility or user adjustability requirements in the occupied space. So how do we make an OPR useful for modular chiller systems? It starts by establishing the project needs, which are most applicable to modular systems. These needs include equipment with bigger turndown ratios and smaller compressor sizes. Therefore, be sure to document how expected use and occupancy will vary throughout the year. Equipment startups with lower condenser water temperature would also be achieved with modular systems. Therefore, it's important to document systems that are intended to have use areas which will require cooling and low ambient conditions. Furthermore, critical systems that require N+1 redundancies should be documented, which would be a beneficial application for modular systems. So it's important that the commissioning provider includes experience implementing modular chiller solutions. Specific attention should be provided to verify that the automatic bypass location is appropriate and a valve and actuator are specified, which are fast acting and are sized for the correct flow requirements. If the requirements are not understood, it is best to act upfront. It's also important to understand how system pressure will be controlled, as well as minimum flow to the chillers to avoid high refrigerant temperature issues or short cycling. Once these parameters are understood, then additional measures should be understood, which reset set points based on the actual demand of the end use equipment. If there are multiple phases, then a plan of action for ensuring proper flows and pressures for each phase and between each phase should be established. If a space is intended to be cooled in a later phase, but not the current phase, then consider installing future chiller modules beforehand, as the cooling requirements for these areas would be picked up by the adjacent spaces in the meantime. In best practice, the commissioning provider should also be included into the submittal review process. These same important requirements should have the same criteria confirmed. An example would be, is the differential pressure bypass selected with the correct CV value, and do the selected actuators have the correct open close timing? So how do we keep the commissioning process on schedule through construction and turnover? Communicate early and often, including at kickoff meetings that are best implemented at the beginning of each phase. Plan and prepare ahead of time by establishing a commissioning plan in the design phase and updating the plan after each kickoff meeting for each phase. Start with the end in mind and stick to the critical path by developing a closeout matrix and listing predecessors for each commissioning activity. When confronted with adversity, ask information-seeking questions. An example would be, when discussing on the status of open issues, request that the responsible trade explains when the issue will be resolved, how it will be resolved, and explain why the issue is critical to be resolved so that all parties understand the importance of correcting the concerns within a reasonable time period. If it's known that critical equipment such as modular chillers will be stored on site for considerable durations, before startup, a plan should be put into place to avoid these machines from becoming damaged. The manufacturer could then provide appropriate guidelines on how to set up the system for longer durations of storage. Some expected outcomes would be to wrap the control cabinets to reduce moisture infiltration and to treat water systems to avoid bacterial growths when stagnant. When dealing with modular chiller systems, start by understanding if the equipment is a legacy system such as a constant volume system. At the same time, request that the latest chemical treatment reports and the latest testing and balancing reports are provided. Then sit down with the control service technician, if available, to understand how the system is operated and currently functions. Also work with the team, including a service technician and vendor, to diagnose any known current chiller issues. Start by reviewing any alarm logs for repeat safety control issues. Have the team confirm proper wiring and power. If the condenser water system is subject to freezing, have the team confirm the proper glycol water mixture and pressure drops across all strainers that are adequate and clean. Once chilled water and condenser water flow and pressures are confirmed to be adequate, also confirm the refrigerant conditions. Note that flashing observed in the refrigerant site glass does not always mean something is wrong. Some refrigerants, such as R134A, commonly have bubbles. However, excessive flashing could also be a sign of a low charge. Always verify that a service technician diagnoses the circuits with a manifold and gauge set to confirm proper approach, superheat, and subcooling temperatures, therefore confirming adequate charge, as well as proper cut-in, cut-out pressure and set points, and that the head pressure is adequate. Incorrect head pressure could mean a clogged strainer or a bad expansion valve. A plan for functional performance testing should be established well in advance of equipment turnover. The parties involved with point-to-point testing should establish a list of points to be confirmed and document that the points descriptions and identifying numbers are appropriate and do not conflict with each other well in advance. A functional test script should be developed to confirm that the sequence of operations meets the design intent. Sequences with change over time and operate through different space conditions should also be verified to be appropriate over time with advanced BMS trending where feasible. And best practice, such as systems serving life safety and critical systems, consider also verifying that full load and part load performance values are confirmed. As previously stated, the sequence of operations are the most applicable to modular systems are variable flow control sequence operations. As previously stated, these allow the system to provide low turndown ratios while responding to increases in end-use cooling demands. Also, as stated, set point reset controls allows the systems to make use of the lowest system efficiencies possible. Although not the only sequence of operations to be confirmed, these are the most important sequence of operations to confirm specifically for modular chiller systems. As previously stated, verifying chiller performance follows a best practice scenario for commissioning modular chilled water systems. Note part load testing requires changes in condenser water temperature, so you would need a plan to establish various loads at different condenser water temperature. So will there be enough load? If not, maybe the team can manually open preheat coils, or if definitely needed, they could utilize small load banks. The team would need to establish a test procedure identifying which set points are to be overridden. A quick way to provide confidence to the team, however, would be to evaluate the approach and delta T across each chiller bundle. As a rough guideline, the normal performance chilled water plant should be providing around 44 degrees chilled water with 2.4 gallons per minute per ton of chilled water with a delta T of around 10, and a 3 gallon per minute per ton condenser water with also around a 10-degree delta T. However, more recent guidelines such as Azure Green Guide recommends for high performance chilled water systems to have a delta T between 12 to 20 degrees and on the chilled water, and a delta T of 12 to 18 on condenser water. The smaller the approach, the more efficient the chiller should be seen to be operating. For integrated part load values, follow AHRI standard 550, 590. This is important for variable chiller systems and is something that is typically, for most projects, verified at the factory. This standard provides guidance for systems with multiple refrigerant circuits as seen in modular chillers, as well as how to determine the fouling factor using the log mean differential method. Also, Azure Standard 30 provides a method of testing liquid chillers, which was last released in 2019. Besides the chillers and pumping systems themselves, heat also needs to be rejected effectively. This is why it's important to also consider verifying functional performance of the cooling towers. CTI cooling tower performance testing standard 202 provides guidelines for verifying proper cooling tower performance. CTI performance is usually verified at the factory. However, for critical projects, an on-site CTI performance test and certification can also be considered. CTI standard 202 provides guidelines on how to reduce drift with the unnecessary loss of water from the tower itself. One thing to note about cooling tower inspections is that forced draft and induced draft cross-flow towers have spray nozzles which should be confirmed to be spraying properly, while larger induced draft counterflow towers have hot decks over the fill instead of spray nozzles. These hot decks include holes for discharging water into the fill, should also be confirmed to be free of any debris. As a summary, a performance assessment requires several measurements to be recorded, including wet bulb temperature of air, dry bulb temperature of air, cooling tower inlet water temperature, cooling tower outlet water temperature, exhaust air temperature, electrical readings of pumps and fans, water flow rate, airflow rate, and if possible, the makeup water gallons per hour. Once these are known, then the performance parameters of defining the performance of the system can also be evaluated. These include wet bulb temperature of air. These include the range, which is the hot water in to cold water out. The approach was which is the wet bulb ambient air in to the cold water temperature on the outlet side, and the effectiveness, which is a percentage which is equal to the range over the range plus approach. Cooling capacity should also be determined, which is evaluating how many tons of refrigeration is provided, which includes your delta T and your flow rates. Evaporation loss can also be measured and defined in meters cubed per hour, which is equal to 1.8 meters cubed for every 10 meter cubed rejected. After that, you can also confirm the cycles of concentration, which is a ratio of dissolved solids and circulating water to dissolved solids up water, as well as any blowdown losses, which is just a function of the evaporation loss all over the cycles of concentration minus 1. Finally, you can determine your liquid to gas ratio. See, the cooling tower incident does provide various charts to confirm your liquid to gas ratio where some of your parameters are not known. All right, thank you. I thank everyone for joining us and being a part of this. If anybody has any questions, myself and Albert are here to answer any of them. Thank you.
Hey, Derek, I have access to the Q&A. I see some questions, and I think most of the questions came up while I was doing the presentation, so I suppose they're for me, and I guess I'll answer them. So I guess I'll start at the top. Have you seen any success with a variable primary pump system pulling out of the chillers in lieu of pumping into them? The answer to that, my answer is yes. And if you ask me for a recommendation, if you recommend pulling through or pushing through when it comes to pump and chiller placement, you can ask a panel of 10 different people and they'll give you a different answer each. I've honestly seen a 50-50 split between people who favor pulling through versus pumping through. So honestly, I at this point, I would recommend just whatever works best for your system, even if it comes down to just the layout of your mechanical space. If you have the opportunity to design your system, if it has to go one way or the other, I honestly can't make a recommendation at this point because I've heard both sides of the story so many times. So Yes, there is success with pulling out in lieu of pumping into the chiller system. Next question. Is this type of system well suited for making very cold water, like for dehumidification at archives? In general, my answer is yes. The reason being, for dehumidification systems, you want two things. On the air handler side of the system, you want very low flow rates, airflow rates, so low airflow velocities. Think like maybe 100 feet per minute on your air handler side. And on the chiller side, you want the water to be essentially as cold as possible. Not like it doesn't have to be like super cold, but you want cold water, and you want consistently cold water. These variable flow systems, one of the good advantages of the variable flow system is its ability to have that supply water temperature control. If you're using a constant flow system, a lot of the times what happens is your leaving water temperature is going to vary, as I illustrated on the previous slide. So when you introduce variable flow design, you can have supply temperature water control, and you can consistently give off that cold 45-degree water, and it's beneficial for the dehumidification processes. And the reason why I say this is an in general answer is because there's many sort of dehumidification applications, and if you're making ice, maybe this isn't the best suitable type of unit. And if you're like, let's say for example, you're cooling computers or servers, and you need a set point to vary no more than plus or minus half a degree, you may want to look into a more a system that kind of focuses on that sort of design. So in general, yes, these systems are good for the dehumidification sort of application. Next question, you talk about minimum flow bypass valve GPM for sizing. Do you have an associated differential pressure across the valve associated to this flow to pick a valve CV? So yes, there's going to be a value, but it's going to also be heavily dependent on the pressure difference or the pressure drop across the air handling unit's coils. So on the previous illustration that I had from the chiller manufacturer, they provided this value for the chiller side DP sensor because the chiller manufacturer knows the pressure drop across their evaporator brazed plate heat exchangers. Unfortunately, they won't have the ability to know the pressure drop across the air handling unit's chilled water coil. So that's probably something that would need to be field configured. Next question, what is meant by wiring the sensor directly to the valve? It seems that it should be just a controller connected to the BMS just like any other, just not dependent on the central BMS programming to respond. Yeah, that's exactly what I was trying to communicate. That's precisely it. So we don't want to depend on the BMS programming to modulate that bypass valve. We want the valve to be wired directly to the DP sensor, and it just communicates directly. The valve communicates directly with the DP sensor, and there's no BMS in between. What are some of the biggest issues you see when starting up and commissioning modular units? Is it getting the min-max flow rates correct, balancing to get the flow DP set points locked in, clean water, controls correctly implemented? Thanks. Yeah, so I'd say those are probably some of the biggest issues we have. Definitely minimum GPM going through the chiller is an issue. If we don't hit that minimum GPM, what happens is you get a bunch of error sensors constantly going off, and it'll be a little bit vague. It'll be something like low pressure, high pressure unit, and it's going to require troubleshooting. So one of the biggest fixes is definitely just making sure you hit that minimum GPM through the unit. That's always an issue. A lot of people, like I talked about before, they program the system bypass valve. They have a BMS programming to respond to open and close that bypass valve, and that generally slows down the reaction time of the bypass valve, and That's very, very commonly an issue. It's very important to not do that and just follow manufacturer recommendations. That's also a very common problem, I'd say. And also just keeping the unit clean, performing your once-a-year maintenance on checking your strainers, cleaning out your condenser heat exchanger, because those also limit performance and make your locked-in set points kind of act up, and it acts up funny. So always recommend your once-a-year maintenance. Off the top of my head, those are probably the biggest issues that we generally see but actually, no, that doesn't apply to startup and commissioning. But yeah, those are usually the biggest issues: the BMS controlling the bypass valve and the minimum flow. We have a request for energy efficiency of traditional versus modular chillers. So, I mean, there's many different ways and many different types of chillers, but in general, it really depends on the heat exchanger and the compressor type you use. So if you use a centrifugal type of compressor, you generally get the highest efficiencies. If you use a scroll type compressor, you're going to get lower efficiencies. A lot of modular chillers use smaller scroll type compressors, so you do lose that initial efficiency, but you can make up for it by turning off and having the ability to modulate to really low efficiency points. If you look at a centrifugal chiller, if you look at its efficiency chart, it starts to lose efficiency around 50% or 40% modulation levels. And when you get down to about 10%, you'll see that you can run it at 10%, it just loses a lot of efficiency. Whereas a scroll modular type of system, if it modulates down to 10% and you have a lot of different compressors, that efficiency level will stay consistent. So it really does depend on the system that you're designing and you're using, and it's hard to compare them heads up because they're two completely different types of systems. But in general, centrifugal chillers will have higher efficiency than scroll chillers that use, and those scroll chillers generally are used on modular. But I did show on a previous slide a modular centrifugal type chiller, so that's sort of the best of both worlds option also. And first cost difference between traditional and modular, I'd say I don't have the numbers in front of me, but modular generally is a pricier option than a traditional chiller. And the reason being is because you have a lot of compressors and you have a lot of heat exchangers. So even though there's smaller compressors and smaller heat exchangers, just based on quantity, they tend to add up cost-wise. And I mean, if you shoot me a message, I could probably give you a more accurate assessment of costs if you're interested. And we have a question for you, Derek. Please discuss the importance of factory startup versus by installing contractor of modular chillers. Or I can tune in also, but if you want to jump in here, Derek.
Yeah, I would say it's important to have a manufacturer's representative there that's factory trained, that actually understands how the thing functions. I've seen, as far as a startup by the contractor, they turned on power to the unit and seen if it's making cold water. It's usually not what you want. But I would extend that, because you also need at start you want to have the controls vendor there, and the system should be at least preliminary balanced at that point, so you're not tripping on flow because you haven't even set pumps at any flow rate yet. And I've seen some problems when the BMS, the control system, wants to use some of the points within the local chiller. So there's some coordination between local points and integrating those points to the BMS. If you have anything to add, Albert, to that, feel free.
Yeah, so I would say that factory startup is generally less inclusive than a full-on commissioning process. So if you look at, I can provide this also if anyone's interested. If I pulled up an installation and startup manual for one of these chillers, you can see it's probably like a page long. It's not very inclusive of the whole system. They just ask for a few basic things. They want to make sure there's electric to the unit, the unit's running, they'll take a test run, and they need probably like 50% simulated load. And they're not gonna, and they don't really care about like, you know, the ambient temperature outside and making sure it's going to work on a system-wide level. It's mostly just to make sure the unit works and everything's installed correctly. And it's just a check mark so that we can start the warranty in case anything goes wrong on the manufacturer end. A full-on commissioning process is definitely more inclusive of, you know, the whole system, and there's differences. So I don't think the factory startup is like, you know, enough most of the time, because there's a lot more to it than that. The factory startup is just a process to make sure the unit works and we can get warranty on the unit. That's pretty much the objective there. Next question, do you have an objection to wiring the bypass valve to the BMS if the chiller DP is also wired directly to the BMS? I mean, I don't have any objection to how these things are wired. The only objection I have is if the reaction time to the system is more than 60 seconds. So if I have the DP sensor wired to the BMS and the BMS is doing some PID logic and it takes longer than 60 seconds to send that signal to the bypass valve, and the bypass valve needs time to also need stroke time, and that whole process takes longer than 60 seconds, then we have a problem. That's and it's honestly a very common problem. So that's why, just as a broad, you know, just as a broad example, I tell people to always just wire that bypass valve directly to the DP sensor. So there's no, you know, logic that needs to be interpreted by the BMS to slow down that whole process, because having a quick response time is one of our key design tips for success. And we have a comment. I agree with the early OPR to indicate optimal efficiency. To test installed efficiency, I assume the best way to do this is by letting it run for a while and then analyzing historical data. Do you have a preferred data history tool or set of equations available online that can be implemented to access performance? If you can jump in here, Derek.
I mean, ultimately, when I went over the part load and full load performance values, which I believe like the vendor would have, but I mean, just from a basics, I mean, reviewing BMS trends and just ensuring that, you know, you're providing the correct amount of tonnage at full load, and you're not having any trips, and you're maintaining, I think importantly, the correct chill water temperatures are the most critical things to see over time.
And depending on the manufacturer, the master controller may have the ability to have historical data on, you know, when the chiller was running. At this time, it was running with these performance metrics, and a lot of times you can also export to an Excel file. And that could be available in the master controller. Otherwise, BMS.
All right. Well, thank you so much, Albert and Derek. We really appreciate your time and expertise. And on behalf of BCA, I'd like to thank everyone for your participation in today's Tech Talk, and have a great day. There's nothing else to add.
Thank you.
Very good. Thank you so much. Take care, everyone.
Have a good day.
You too.
Bye.